The next one is UML.
So let's start with the document which explains UML. It's a standard. It's something which is already standardized, and long time ago, about 15 years ago. Why I decided to put this quote for you? Because it says that the primary audience for this detailed description consists of people who are not normal people, like tool builders, standards organizations, methodologists, experts, whatever. So people who, readers looking for an introduction to the UML, should consider another source. So UML is, on one side, it looks like a very simple notation for drawing pictures. But on the other side, deep inside, it's very large, huge standards, and actually family of standards, how to present information. And they suggest us to present information so that we can exchange information from one developer to another, from one team to another, the information about our software. So UML is something which helps us to explain our software. And actually UML is based on XML, which shouldn't be a surprise for you. So all the standards, all the formats we're going to discuss today, they are all based on XML. So XML is helping UML to exist. And it's difficult. It's super difficult. If you get into UML modeling, like really modeling, then it will be extremely, at the same time, it's not messy, I would say, because it's quite, in my opinion, it's quite well designed. It's quite well designed. They are UML territory. They have well-designed standards, but they are really complex. The complexity is pretty high. So we're going to talk today about, first, class diagram. What it is, basic elements. Then I will show you some other diagrams, which you need to know. You can research yourself more. Then we'll talk about these things, the elements of model-driven architecture. I'm sure not so many of you actually know what is model-driven architecture. And we will talk about MOF, XMI, OCL, QVT, executable UML, and maybe something else. Then books and everything. So basically, three important things today: class diagrams, other diagrams, and then model-driven architecture. Class diagrams, that's the easy part, the easiest part. We will talk about what are the classes, generalization, composition, aggregation, association, and dependency. First, classes. Document, book, email. Probably you understand what it is, right? Can you explain the difference between these three sections in each rectangle? Why we have one section, another section, and three sections? So each class is basically three parts. So what are these parts? Do you know? Say again, name, attributes, and operations, or maybe methods, whatever. So what these pluses and minuses mean in front of the attributes? Prefixes. Private and public, right? The visibility, they say it's a visibility. So that's pretty much all you need to know. Can you explain the arrows there? One arrow, another arrow, what do they mean? Generalization. And what is generalization?
Document is parent of book.
Document is a parent of book.
It's an implementation of inheritance. It's that one component, one class is a specific form of one general form.
Right, but it's not necessarily. It's one component is it's more specific form of a more general form, right? But it's not necessarily mean, in my opinion, inheritance, implementation inheritance. It means maybe more like subtyping. So I would say that this relationship generalization, which we will discuss in a second, this generalization, in how I understand it, it means the relationship is a. So we're saying polygon or ellipse is a shape. So we're like specifying more specific definition, but it doesn't mean that we use the inheritance like in C++ or in Java, like inheritance. So it's more like subtyping. Subtyping means like, I am a human, and the human is an animal. So that's the relationship. So between me, human, and animal. So we are is a. This relation is called is a. Is dash a. So I am, well, this is a human. This is an animal, and so on and so forth. The same here. The shape is like a parent, more generic form of something, and then polygon is more specific form of something. So that's class diagram. Next one is composition. Composition, take a look. It's a window. The window, there's a slider, the header, and the panel. So what does it mean? Who can explain this diagram? Who knows what's... Yeah, go ahead.
Inside the class window itself, you have three attributes which are scroll bar, title, and body. So basically, we can use the functionalities of these attributes, of these classes from the class window itself.
Yeah, that's right. So the window is a class which has three attributes, and each attribute is it's
Just now, important moment is that composition, let me say that they use composition, they mean that, for example, slider cannot exist without window.
That's right. That's right. So that was my question. So I wanted to ask you why these diamond symbols, they are solid. They're black. That means what you just said. That means that the composition here means that the window cannot exist without a slider. The window cannot exist without a slider. So the slider is an irreplaceable element of the window. So window, they always, like if it's a human, then it's like a hand there, or a leg there, or an eye. The same here. So it's something which is unreplaceable. If the element would be empty, that would be, what is it? Aggregation. That's right. So the difference between composition and aggregation is that aggregation is like, okay, there's a class room and there are students. So that's aggregation. If you all walk away, the class will still exist. It's a perfect class with no students. But in this case, the window may not exist without a slider. And actually, it says here that, what are these numbers? 1, 2, 1, 1, what do they mean? Do you know? Arity, that's right. Arity of the relationship. So in this case, we say the window must exist with exactly two sliders. So one window, two sliders. So if you look at the slider, if, for example, you look not from the window, but you look at the slider, then you can say, okay, I have exactly one parent. I have exactly one element which I belong to. So the slider cannot belong to multiple windows, but the window may have two sliders, must have two sliders. The aggregation is the, if you look at the top left corner of the diagram, you can see team, and the team has this sub-relation sub-team. Who can explain what this means? What is this sub-team text here, and builds, for example, and sub-assembly, assembly, what are these texts? They stay here, look at this diagram, and then look at this one. So we have here also scroll bar, title, body. You see? They're attached to lines. Here they also attach to lines. So what are they?
So each team can be a sub-team of at most one other team. And one team can have from 0 to any number of subteams.
Exactly, exactly. So this relationship means that the team may have 0 or 1 sub-team, and the team and the sub-team may have exactly the other way around, right? Okay, and how would you implement in Java the aggregation? That's a tricky question for you. So here the composition, I understand how to implement it. So I can easily turn this code into Java. So I will say I have an attribute title, and the type of the attribute is header here, right? So something will be attached there. So the object will, there will be my child object, that will be the attribute, right, in Java. So how I would do it here to implement this empty diamond symbol? What's going to be the difference between this implementation of the attribute, body or title or scroll bar, and this one, subteam? Because subteam is the name of the attribute. Subteam is the name of the attribute as well for the team. So the team will have an attribute subteam, but it's an empty diamond. It was the solid one, now it's an empty. It was a composition, now it's aggregation. So they will ask you, okay, what about Java? Conceptually, we understand the team may have zero, for example, the students may have 0 students. Second? Exactly, null reference. Nullable reference, yeah, exactly, nullable reference. So in this case, we say composition means not no nulls ever. So it's strictly, we have a slide, we have a scroll bar, 2 not nullable elements. We have a title, you cannot set null in there. So it has to be something which you set there for sure in the constructor. Here we say, okay, sub-team, no team, it could be null. That's the difference, composition, aggregation. We discussed null in the previous lectures, null is bad, so aggregation is bad. If you aim for good design, then don't do aggregation. The rest is the same, 0, and would you understand the star, right? 0 dot dot star, what the star means? Any, yeah. Sometimes they use stars, sometimes they say n, the English n. Sometimes you can see 1 dot dot n, means the same as star. Association, company, person. So where is the association here?
Solid line.
The solid line, exactly. Between employer and employee, that's an association, and the association has a name. What's the name of the association? Job, exactly. So job is the name of association, and this dot line actually explains the association. So association is called the job, and that's a relationship between the company and the person. So how is it different from this one, for example, from aggregation?
Name of attributes of the job.
Say again?
Neither of these classes contains other as an attribute.
Yes, exactly. That's the difference. So company doesn't have an attribute employee, and the person doesn't have an attribute employer. So they don't know about each other. The company and the person, they don't know about each other. They don't have attributes there. We have another extra class which knows about them both. So you talk to the job will tell you, okay, I know who is the employer, I know who is the person. But if you go to the company and you go to the person, they will not know about each other. So that's the association. So association happens through some other class. And yeah.
Explain how this again can be done in some.
How in Java, yeah? How to do association in Java. So in association, to implement association in Java, for the company we have just a normal class. For person we have a normal class, no extra attributes there. And then you create another class, which is called job, with 2 attributes, employer and employee. And you have them, these objects in there for these attributes. This is how they do in relationship databases, these connections between tables through associations. Dependency. What is dependency? Dependency is where we can find dependency here, well, actually everywhere. So they are dashed lines. The lines which are dashed lines. Dependencies are, how can we implement the dependency between here, like class A and class B? It says friend. How do we do it in Java? Instantiate, refine, call. There is no way to do it in Java aesthetically. So I think as far as I understand, these dependencies are more about dynamic relationship. For example, I say class A calls class C. So I set it like a dependency. So these lines in the diagram, they are more for information. They are more like giving the information about how these things will work in runtime. Not how they're structured, not how they depend on each other. It's more about how they work. For example, I say, I want to give you an impression of how my classes interact. So I say, this one will call that one, this one will call that one. And you know about this. But it's not going to affect the way your classes will be designed. That's how I understand. That's it about class diagrams. Who of you ever used class diagrams? Really? For your projects?
Several assignments were required to use.
Okay, so you had it during the study, right? And did they check your diagrams?
Kind of.
And And there were mistakes, they were correcting your mistakes, like something is wrong or what?
Which corrected something from IT, so.
You just generated, yeah? Auto-generated, yeah? Okay. Okay. Well, all right, so let's see other diagrams and then I'll show you what these diagrams were invented for and like originally. Some other diagrams. We will talk about use case diagram, component diagram, deployment, activity, and sequence. 5 types of diagrams. And then we make a break. So first one is use case diagram, which is in my opinion completely useless stuff. I don't know. I mean, it's fun, it looks nice, but I don't see what is the purpose of this? Because I believe that, we discussed that before, that use case or user stories, use cases, they must be written in text. So each use case is a text. The text explaining the story of how you interact with the system. It's a storytelling, it has to be in text. Making this like these circles and saying, okay, cancel appointment, the patient can cancel an appointment, nice. But what kind of information it gives me? I mean, maybe it's okay to just oversee the whole system and say that yes, the patient can do 4 things: cancel an appointment, make appointment, request modification, and pay the bill. But we can do it in the text as well. I don't see why we need diagram, but it's very popular. Usually people start with use case diagrams when they learn UML, so let's learn it as well. So this rectangle around all the use cases, what's the name of it? System boundary, usually they say, system boundary. So it's a border. All the actors, they should stay outside the border of the system. So we do not move actors inside the border. That's the very idea of use cases. So all the actors, they always interact with the system from the outside. And actually some people, including myself, they believe that the system itself has to be an actor. So the system which we design has to be an actor as well, has to be present on the diagram as an actor. And actually there are 2 different, approaches to this. Some people believe the system should not be the actor. Some people believe that system should be the actor. And I usually ask this question on the interview when I interview somebody who claimed to be system analyst, because people who design these diagrams normally in rational unified approach, they are called system analysts. So people who analyze the system, and they're supposed to design requirements like we discussed on our first or second lecture, and they need to present the use case diagram. And they need to know the system. Is it an actor or it's not an actor? So I ask this question, and if the person says, what do you mean? I don't know, then it's one answer. But if he says, she or he says, it has to be an actor, and I say why, and then there's an explanation goes, then I understand that this person knows more or less about use cases and requirements. So you also have to know. So there are 2 approaches. First approach, system is an actor, means that when we design a system, then the actor, the patient, for example, to cancel the appointment, the line goes to the circle, and then in this circle, all the actors who interact must be connected. But the actor, the patient, interacts with the computer. So this interaction has to be by both actors. So for example, I have a phone, let's say I upload my picture. So I click the button, I submit the picture, and the computer takes the picture and uploads it to somewhere. So I interact with the computer. And if you read the use case description, there will be actor can do this. The system will do this. The actor will do this. The computer will reply like this. So it's interaction of two entities, human being and the computer. So why in this diagram we should not draw the same picture for the computer and let them interact through the same circle? That's how I understand use cases. Not only me, many people would say this. Other people say that's nonsense, so we don't show the system because the system is always intrinsically there. So there is no other way for people to interact with who. So we just assume that the system always stays behind this every circle. That's the second approach, how I understand it. Okay, so we have these circles for use cases, and we have this relationship include. Include one use case can include another use case, meaning they're like subroutines. That's exactly the same. So one use case, for example, in order to make an appointment, you need to check whether the patient is there. So it's basically in order to reuse some subroutines, some sub-use cases. For example, yeah, in order to register a patient, you need to check for his or her a photograph. So checking this photograph will be the procedure which is used in many cases. To register the patient, to pay the bill, to do this and this. So you move it outside and call it sub-procedure. That's it. Any questions about use cases? So try to actually draw it. I mean, it's fun. Anyway, yeah, no, it's not fun. What? You did it, yes, so enjoy it. Next one is the component diagram. Do you see it? It's quite small. The component diagram is the diagram where we put software components on the paper, and then we connect them through. How do we connect components to each other? Through what? Through interfaces, exactly. Each component gets connected to other components through a number of interfaces. What are the interfaces? They could be API, they could be interfaces could be different. For example, it could be a connection over the internet, over the network. It could be the connection over the inter-procedure connection inside the same runtime. It could be the connection through, I don't know, through files, through command line shell, through different things. These connections could be different. So when you draw the component, it's a rectangle with a small icon on the top right corner. That means the component. The component is something which is compiled and deployed to production. So it's not a class. It's not a group of classes. It's executable piece of software. .exe file, jar, the compiled Python. What's the name for compiled? What Python? It doesn't compile. No, it does compile.
Well, you can, but it's
Compile it into the bytecode, so if I see.
Yeah, exactly.
It's not usually done.
It's interpreted.
Yeah.
Okay, nice. Okay, so if it's interpreted, but then we can call, in case of Python, we can call compiled something. Well, we can call, component. So what is a component in case of Python? The component would be a big collection of .py files, probably. So in this case, it's more like, it's not so easy to make a distinction, because in case of Java, you cannot say that my 100 Java files is the component. You have to compile it and say, okay, this jar is more or less a component. So a component is a runtime creature. Component is not something which is in your source code. It's something which you get in runtime when it starts working. That's how I understand the component. And they have interfaces. So when the component is working, it's listening to us asking questions. And we identify those interfaces like the line and then the circle. So we say this is we provide the interface. And when we use the interface, then we show it like this. So if, for example, two components state and one component gives the circle as interface provider, so I am listening to you. And another one is consuming the interface. That's component diagram. That is quite interesting too. And you see components can go inside other components. One large component can have a number of other components inside.
But why we have like different implementation between different subsystems, and for example, we have shopping cart and authentication. So why we use different implementation for this implementation?
We have different notation for shopping cart and for... Yeah, show me.
So we have interface here.
Yeah.
And it's not this way. We have interface here as well.
Oh yeah, there are different notation.
What's the difference?
I think it's exactly the same. It's because they're they're trying to put these components far away from each other, and that's why they use different notation for connecting them. But it's exactly the same. I am 99% sure. Maybe I need to double check. Deployment diagram. Deployment shows how we take these components and place on servers. That's simple as that. So each server is a box. Server, mobile phone, laptop, like some hardware device, whatever. Each place is the hardware. This box is a hardware. And deployment diagram helps you understand where your components will be placed, in which boxes. So you say, oh, I have a mobile phone. Into a mobile phone will go my APK, this APK, right, on Android, APK file. So APK file is the component, the box is your mobile phone. So you draw the box and say, this is my mobile phone component, you put it inside this box. That's it. That's component diagram. Sorry, deployment diagram. My bad. Activity diagram. Activity diagram is when you explain how things work in terms of an algorithm, I would say. So you start. Do you know what this solid black circle means? Entry point, the starting point. And the circle with another circle is the exit point, it's the finish. So this diagram explains what's going to happen from the beginning till the end of some algorithm. We start with a solid dot and we finish with another dot and we go step by step. And we have these lines, solid black lines, they call them, I'm not sure, a synchronization line or something like this. So when you put this vertical line and then different arrows enter this line, it means that all of them should finish at the same time. So we go parallel, for example, we do something and then we finish on one line and then we again can go parallel, like in this diagram. So every box, no, the box with the rounded corners, actually each box is some execution, something which has to be done. And then every diamond image is what it is. The diamond. It's forking. Yeah, it's just basically forking, going into different directions. And what this interrupting edge, okay, I didn't know about that. On top right, interrupting edge. Swim lane. Swim lane is an interesting concept, so you can look at you see this, the whole diagram is divided into three swim lanes. So the lane goes, the first lane, the second one, the third one. On these lanes you can have different activities, and then you can, it will help you imagine different parallel processes happening at the same time. So this type of diagram is I believe, if you ask me, I think that this one and the next one, the sequence diagram, are the most necessary in the whole family of UML diagrams. Probably sequence diagram, the next one, will be, I believe, the most useful. When I say the most useful, I mean we need the most, because we can survive without the component diagram. It's not a rocket science to understand that APK file goes to Android phone. You don't need actually to explain it too much. You can just say it in the text. You don't need a picture for that, in most cases. For the component diagram, okay, yes, we have APK, and this APK talks to Android through Android SDK. It's more or less clear. You can say it in the text. The class diagram, you open the class, you can see the attributes, that's all. You know what they are connected to. So many classes, I don't think that's very important in most cases. In most cases, that's being used in order to impress your customer. So you want to present proper design documentation or impress your teacher. So you present the documentation, you make these diagrams just to make it look nice. But this diagram, the sequence diagram, this is where really people, talk to each other through diagrams. So if you have a team of programmers and you want to explain to your team what's going on, instead of dancing in front of the whiteboard, you better draw them a sequence diagram. You better show them the diagram, and that will explain more than your words. So how it is designed, this diagram, you have this also, I think, swim lanes, which mean time. So time goes from top to down, which is maybe a surprise for somebody. So time goes like this, in this direction. Each swim lane has an actor on top, somebody who is acting, who is working with other actors. So in this case, we have 4 actors, 4 creatures, which could be different things. It could be components, there could be classes, there could be objects, depends. Here we have the window, JavaScript, servlet, proxy, whatever, different things. And then you start from the left to the right, you hit the swim lane with a message to the actor. So you start talking with the actor. The actor goes down doing something with your message. And the actor can go to other actors, talking to them. And they can go also talking to somebody. And then eventually it goes in parallel. eventually the diagram may look quite complex, explaining the things which happen in parallel. We're not going to discuss what's on the diagram, that will take more time than we have, but you definitely, I suggest you definitely try to create this diagram for your project, at least one, explaining how the things interact. When I was passing, I think I told you that I was like about, I don't know, 8 years ago, I was getting the certification from Oracle for Oracle Certified Master. And in order to get this certificate, you need to pass the exam at the examination center, and then you need to write like an essay explaining something, I don't remember. And you need to do the homework, you need to do the assignment, like you do for your course. They also sent me the problem, the description of the project. That was like some online shop for pets. So like you can go online and order some cat or dog, and then we basically place this order and ship you the dog or something like this. And the requirement was that as part of my design description, it was not necessary to write code. So I was not required to code. I was required only to provide them design documentation. And in this design documentation, it was absolutely mandatory to have class diagram, component diagram, deployment diagram, and at least one sequence diagram. So that's how Oracle thinks, what Oracle thinks are important for design description. Sequence diagram was right there. So that's why we study, and probably use case diagram as well, I don't remember. But sequence diagram is something that will help you explain to other people how your things interact to each other in time. So model-driven architecture, that was the idea, still is the idea, that we may develop our software not like we normally do now, when you open the editor and start writing your Java code or Python code, but you do it differently. You do it in 3 steps. Well, no, not necessarily 3 steps, but the main concept is this. You design your software using UML. So you put the class diagrams, you put the component diagram there, you put all the links properly, like the specification wants. Not just a picture, not just a nice drawing, but really connecting all the elements together, which is called, on the left, called CIM, so Computation Independent Model. So you don't say in your diagram how it's going to work in a real like programming language. You say it's computation independent model. So you're making the concept of how your software works. For example, you design the use cases and say, okay, the patient will come in, it's going to be use case, register a patient. And then you design a class diagram. You say, I have a class called patient. And then I have a class, I have a class registration, like register in the database. And another class, which is a ticket for the patient, and so on and so forth. So you put all the elements together conceptually, without computation, without writing even a single line of Java code. And then the next step, we click the button, the magic button, and the software converts this diagram, this set of diagrams, into platform-independent model. Platform-independent model. So there is still no classes. There's still no Java code, but they're more specific. Or maybe you don't click the button, because on the diagram I can see that on this step, this process independent, platform independent model, we have class diagrams, we have object diagrams, timing diagrams. Okay, so we probably can combine this CIM and PIM steps. So we together design the model. That's the idea. We design the model, and then we click the button, and boom, the code is right there. The Java code, the database model, all the documentations, everything is ready. And it just magically starts working in production. Well, of course it doesn't, right? So we all understand it's not going to work. And then we look at what's going on there, and instead of fixing the Java code, we just understand, oh, probably we made a mistake during the design of use cases. So we go back to the model, we a little bit tweak the design there, we change some diagrams, then we click the button again, and the whole thing goes to production again. And again, it doesn't work. And again, we don't touch the Java code. We go back, and so on and so forth. That was the concept many years ago about model-driven architecture. So we are driven by the model. So the model, the pictures, this is what we work with as programmers. Of course, it didn't work. I mean, for obvious reasons. I mean, I'm not really a big like expert. I actually tried that. It was really intriguing. I was really intrigued by this concept that we're not going to write code anymore. We're only going to draw diagrams. That's so perfect. Everything will be automated. But in reality, it didn't really work. In reality, the key problem is that when you deploy, you see the code, you jump into this code, and you immediately start fixing it manually. And your code goes away from your model. So the model are good pictures, but the moment you generate the code, you see that it's much faster for you to change that code instead of going back to the model and fixing it. So it's not enough discipline. I believe that's the reason why this MDA concept now doesn't really work, because we are not so disciplined, we're not so organized that every time something is wrong there, we're going to go back to diagrams and only work with the diagrams.
But is it possible to do it the way around? So, for example, if we create a model, and from it we generate the code, then we see some bug, we fix the bug, but again, after fixing the bug, this code will generate the model.
That's a good idea, I understand. So let's say, I can repeat that. So we take the model, we generate the code, there's a bug, so we fix the code there, and then we click some other button, and the changes go back to the model. That's a good concept, but I haven't seen it in action. I don't think it's possible, because the model generates something down to the low level of Java programming. But imagine how difficult it is explaining everything in writing, in diagrams. For example, we have a very simple algorithm, Fibonacci. The Fibonacci algorithm, we can explain this algorithm in sequence diagram and class diagram, put this together the diagrams. But it will be difficult to do it in diagrams. You need to really be professional diagram expert to explain even this simple algorithm, which is 3 lines of Java code, to explain it in a sequence diagram or activity diagram. It will take much more time than to write this code in Java. Much more. It will be very expensive. So anyway, I don't know exactly why it didn't work, like specifically why, but I feel as a programmer, being a programmer, I feel like it's just not natural for us programmers to work with the diagram and specify our thoughts in images, in rectangles, in arrows, comparing to just typing the code. So we are, by design, we're more like hackers instead of like designers. Very few people can think systematically. Very few people can really think through diagrams, can really think through strict and formal and clean notation. We are like, whatever works, put it to production, click the button, let's go home. That's our mentality. So this model-driven architecture was perfect idea, but still we're going to discuss its elements. The element number 1 is called Meta Object Facility, MOF, Meta Object Facility. That's actually, let's see, read the text. The Meta Object Facility is the main specific language used to define meta models, just as EBNF is a DSL for defining grammars. Question number 1, do you know what is DSL? The main specific language. Can you give an example of DSL? SQL, that's a good example, yes. Anything else? Do you know systems probably, any of you are close to DevOps? Some of you. Do you know systems like Puppet, Chef? You know Puppet, yeah? So configuration management, yeah. So Puppet and Chef, there are systems, I'm not sure about Puppet, but Chef is definitely written in Ruby, maybe Puppet also in Ruby, I'm not sure. So Ruby is a language which is very good for designing domain-specific language. So you take the syntax of Ruby, and then using Ruby, you define a new language, which is very simple, which understands probably 5, 6 commands, but these commands are very specific for your target domain. So this Chef system, which allows you to design configuration for your servers, is written in Ruby. But when you write scripts for Chef, it doesn't look like Ruby for you. It looks like some new language. But if you look deeper, if you see what's going on, then actually you're writing Ruby. But Ruby is so flexible in syntax, so you can remove all the brackets, remove everything. So in Ruby you can design, you can make, you can implement libraries or certain classes in Ruby the way that people will be able to say, hello to you, my friend. and the system will say hello to you too. But hello to you, my friend, they will be methods of some classes or class names. But put together through spaces, Ruby will understand it as class.class.image.method.variable. So all together, it will be executed through Ruby compiler and will turn into a normal execution of methods and classes. So this is domain-specific language, which is one example is this Chef. Or maybe another example is SQL. SQL is more like a language for a specific case, but we can call, Java is also language for some specific case, but we don't call it domain-specific language. Domain-specific language, usually it's a language which is very simple, very narrow. It can do just a few things, but very well suited for specific application of your inside your application, for specific corner cases. So MOF is MOF. This has a number of layers. In order to explain what it is, I'll say that UML says that you are allowed. Let's put it this way: in your diagram, you are allowed to have classes and arrows between them. UML says this. And then the question is, what are arrows and what are classes? So we go to the next level of abstraction and we say classes are rectangles and arrows are things that have two corners and the line between them. These are the arrows, these are the classes. These are the arrows, these are the rectangles. And then the question is, what is the rectangle? The rectangle is something that, and so on and so forth. So we go to meta layer, meta, and so on and so forth. So on the lowest level, we talk about classes, aggregation, composition, and things which are understandable by human. And then on the next level, on the next meta level, we need to explain to the computer what do we mean by class, what do we mean by rectangle, and so on and so forth. Maybe my explanation is not perfect, but I'm thinking what kind of metaphor to give you so that you understand. In this case, okay, let's take on this example. They say you have, in your diagram, you have a person and you have a name, for example. The person can have a name. And then you go to the higher level, and then the question is there, what is the class? What is an attribute? What is the relationship between them? And then you go to the higher level, and then you question, what is in general, what are the concepts which we deal with in this model? So they're like trying to, MOF is like a definition of the definitions, or definition of the language. Too many words, I believe it's completely ununderstandable, but I suggest you to Google it and read at least once what it means. Next, what I would like to show you is XML metadata interchange. So look at the diagram. The car, the owner, the car has the manufacturer, the string, the owner has a name, they have a relationship or one to another, which is probably the relationship of it's probably the association, because the owner, neither owner nor own cars, or maybe not association, probably it's a composition or aggregation, it's an aggregation. So what you see below that is the formal description of this diagram in UML. So XMI is the language in which you explain the UML diagrams. So when you draw the diagram, if you go to any UML editor, in the editor you will draw the diagram. In most tools, you will see the feature called export to XMI. So you can draw your diagram and then click export, and XMI file will be generated. And this XMI file you can send to somebody, that somebody will open this file with a different tool, and it will be opened, and the same diagram will be right there. So that's the beauty of UML. So UML, like I told you in the beginning, it's not just the language of pictures. It's not just the description of how you draw your pictures. It's actually a formal specification of your diagrams. So you put all these elements together, then you get it exported to XMI, and XMI is more or less formal description. So now you can apply whatever you can apply, it's XML. Yeah. How to use it? That's a good question. So what do we need it for? Original idea from model-driven architecture was that you design everything, then you generate XMI, and then from XMI, some other tool will generate Java code. Or for example, you generate this XMI and another tool will jump in and say, your diagram is wrong. You did something wrong because I don't think that car can be related to the owner in this way. You forgot to mention the arity, for example. So you can do some sort of a static analysis over this XMI. You can statically analyze your model because this is the model. This is the model of what is there. So you can run some analysis on top of this model and say the model has problems, you can even transfer the model. And we will discuss it right now. So what to do with the model. There are a few things you can do. First thing is there's a language called Object Constraint Language, OCL, which you need to know that it exists. So this is the example of this language on the bottom. So we have another set of elements. We have a vector, and then we have some activity diagram for the vector. So at the bottom we say the language, which is the programming language, which says, in this context, when you call remove element, if the precondition is it's not empty, and if in the beginning it was not empty, then at the end the size, and then the size before the execution was 1, it implies that after the execution the array will be empty. You don't need to understand like literally what it means, but this is the language which manipulate the elements of UML diagrams using XMI. So if you convert the UML into XMI, and then together with the OCL, we will be able to make expressions on top of UML. So the idea of people who invented this was like that. So we're going to design our diagram in UML, and then we programmers will just go into these diagrams and write some code in OCL, not in Java, but in OCL. The code of we will write some programs on constraints. We will say that you know what, this array will never be empty. Or make sure that after you call this method, in the end, this object will never be in the state of this. Or make sure you never access this entry point of this sequence diagram, blah, blah, blah. It's supposed to be long texts of constraints on the diagrams. I mean, it's complete utopia, in my opinion, but that's what this OCL is for. To look at the diagram and add some logic to the diagram in terms of diagram elements. So you don't code in Java, you code in these blocks, in the blocks of the diagram. That's what OCL is for, Object Constraint Language. So you make constraints on the objects, on the diagram. Another interesting thing is QVT, Query View Transformation family of languages. QVT is basically a language, but there are many other languages which do the same. That's an interesting idea. Actually, when you can, for example, on this example, on the left you see the meta model. It's the model in UML. You say we have this, like, for example, this is the meta model, really. So the idea, don't look at the diagram, the idea is simple. For example, you have you draw your UML diagram, which explains I have customers, I have patients, I have some data, I have something else. So you put together, for example, the class diagram. And then you click the button, and using the language, QVT, we do the transformation of one model to another. So from this model, we, for example, generate the model for a relational database in just one click. Model to model, model transformations. It was a huge area of research about this, how we can transfer one model to another, and then maybe backwards. So what to do with the models? So instead of discussing whether our system is good enough or not, we can instead deal with formal specifications and languages which are strict enough. I can give you a practical example why why these people who invented this probably needed it for. So let's say you deal with a large system, enterprise system, not just a small web application where just a few buttons and like Instagram or whatever, but a large enterprise application. For example, you need to automate the work of this university. So you have the many forms, many data structures, like information about students, about courses, about professors, about timelines, money flow, medical information, payments information, different things. Imagine that's a huge database. That's a huge database, a lot of data, and many processes. So many things happen with this data. So you will have tons of use cases. You will have tons of classes. You will have many things in your system. So somehow this has to be explained. It cannot be just code. So you need to explain how your system works. And if you explain it properly in the models, so you design these many diagrams, and then you make these diagrams in UML, and then you can store these diagrams in XML, then imagine that we have a tool which will look at this system and automatically will say, for example, transfer this to some other model which will, I don't even know what it could be, this transformation. For example, it could do some optimization of the model. Maybe it can say, I can find a way how some processes can be optimized. Or I can say how you duplicate things. Or maybe I can transfer this to, to relational database. So instead of you manually designing all the tables in the relational database, I just click the button and it takes your classes and suggests you the model for relational database. Maybe like this. I don't know, it probably worked for somebody, but never worked for me. And the final idea, which is called executable UML. The language is FUML, or now we have a more modern language called ALF. ALF, I checked it, the last time I checked it was in some development about 4 years ago, so it's not really dead. Because everything I showed you before, this stuff is close to dead, in my opinion. So if you check the standards, they're published like 10 years ago, 15 years ago, all the work is like outdated. So modern development, in my opinion, is not using this stuff. But this is more or less active. So imagine that we have we can write the code in terms of executable UML. So we write, so we using the diagram, we'll look at the diagram, and then using the things from the diagram, we write the code which can be executed just like Java. So we don't need to take UML and then convert to Java and then execute. We can just, using the things which we see on UML, we can write the code which looks like Java, which looks like the normal, procedural / object-oriented language, and then we can execute it, and it will work. Something like that. I have no idea who used this stuff, but you need to know about this. So all of this garbage, it's not garbage, sorry for saying that, but all of this stuff is, is from the family of model-driven architecture, which was a huge trend 15 years ago. Now I think it's not a trend, but you need to know that it existed. That UML is not just a language, it's not just pictures. UML is a large set of family of standards which were designed, well designed, for explaining the design formally, and then manipulating with design. So you draw the design, you send me the model, I run some scripts, and maybe the model is transferred a little bit. For example, I find the mistakes in your model, I can optimize your model, but we talk formally. It's not like you draw me on the board like this and explain stuff like this, because this is informal. But you send me the XML file, I open it in my editor, and I click some buttons, and gets converted, expressed. I don't know, I can calculate the performance of the system, I can calculate the stability of the system, I can predict the stability, I don't know, many things, if everything is formally explained. Try it, maybe it will work for you. Okay, some books, we're finishing. Book number 1 is definitely UML Distilled by Martin Fowler. 100% you have to read it. It's very easy. Simple to read, easy to read. It's written in a simple language. Nothing will be about this XML stuff, if I remembered correctly. It will be mostly about how to use it for drawing pictures and explaining your thoughts. The second book, I didn't read it. I have to admit, this one I didn't read, but probably it's the best about MDA. So at least once you need to check it so that you know what's going on. Also, I suggest you, instead of the venue, I suggest you to get this certification. I got it long time ago, and it was pretty interesting experience. Actually, in general, I told you about this already. In general, I suggest you to pay attention to certifications. I suggest you to pay attention to actually 3 things in your career, so that you spend the next 3 to 5 years to become the programmer who gets 500,000 rubles per month. So how do you get this? I suggest to focus on 3 things. The first one is open source, that's for sure. If you get open source reputation the next 3 years, if you become the open source contributor in some large project, it's guaranteed that your money, you will get the salary higher than everybody else at your age, at your position, at the same company. That's one. Second, I suggest that you spend time to get certifications. Java certifications, UML certifications, all kinds of certifications. When you will prepare for them, you will get a lot of knowledge and you will get a formal confirmation that you are one of the best. Because look around, how many you know Java certified programmers in Russia? When we hire people, I ask this question, and 1 out of 10, maybe even less, say that yes, I have a certificate, maybe 1 certificate. 1 person out of 10. And we pay attention to these people because we understand that these people passed exam, difficult exam. You know, it's much more difficult than sitting here in the room and just listening to lectures. Because here I know, okay, so you get a graduation from the university, we understand that it's not so difficult, but for the exam, it's something you have to pass in front of the computer. And you need to prove to the computer that you understand Java or Python or some other programming language, or UML. So in order to get this badge, in order to get this certificate, I spent like probably 2 months for preparation. I read everything about UML, about all diagrams. I remember that I remembered a lot. Now I forgot a lot of these things. But I remember that while I was preparing for this certificate, I learned a lot about UML. So I suggest you do the same. And number 3, you can guess what it is, what I suggest you to do. Open source certifications, Stack Overflow. I strongly recommend you to grow the reputation of Stack Overflow. Who has any reputation there? Like what, 1,000? 100? 300? Okay, get at least 10,000, and that will be a sign that you're one of the best programmers in the world.
I saw you have like 17 million.
You have like 17 million programmers in the world. Yes.
No, like your Stack Overflow has something like 17 million.
No, they're not million. I have close to 100,000.
No, something else. It's like views or reach.
I don't pay attention to this. You pay attention to reputation points. Yeah, reputation points. Yeah. So you get 10,000 and you're super cool. So that takes time. That's not so easy. So to get a reputation on Stack Overflow, you need to know how to answer questions to other people, how to help other people, and how to ask questions. Asking questions is also a tricky part. It's not so easy. Try to go to Stack Overflow while working on your projects right now. Try to go to Stack Overflow and post questions there, like how to do this in Python, how to do this in Java. They will be downvotes. You'll be blocked. The questions will be, you probably know what it is. Questions will be... Questions will be deleted, of course, because you don't know how to ask proper questions. You don't know how to formulate your problem. That's a skill. And when you get the reputation of 10,000, then it means that you have very strong skill of how to communicate with people who don't know you, how to communicate with people who don't want to know you, who don't want to like you. They're just complete strangers, and some of them are pretty aggressive, like administrators who just, who are not really willing to help you out. If you watch my YouTube channel, you can see that I had an interview with the founder of Stack Overflow, with Jeff Atwood, just a few weeks ago. I was interviewing him. So we were discussing this, like what it's for, how it works, and he said that many times that this is the source of training for you, the source of learning the skill of communicating with people who don't know you, which is impossible to get in any real work. So you get to the company, you sit in the office, there are 3 people, they like you, they have to like you, they have to respect you. So it's not an aggressive environment like Stack Overflow. Nobody's gonna downvote you in the office. They will listen to you, they will answer your questions. Like I'm here, I'm listening to your questions, I'm on your side. But on Stack Overflow, nobody's on your side. If you ask the wrong question, they just downvote you, delete the question, go home. Absolutely, you just lose the reputation. So no mercy for you. Nobody gonna try to help you. So you need to really be professional, really careful on asking questions. So your reputation on Stack Overflow, for me, when the person comes in as a candidate for a job and I see the reputation there over 10,000, well, I have to be honest, I see probably, I don't know, once out of 100 candidates. Because somebody with a reputation 10,000, that's a person who can, we are looking for these people, not they are looking for job, but we are looking for that kind of people. Why? Yeah, because we know that these people have the skills of dealing with problems, of dealing with people. So these people can work. If something will be wrong, if something will not work for them, they know how to find help. They know how to help others. They know how to provide help and how to ask for help. They have good soft skills. Soft skills is the ability to work with other people in your team. It's not, now in modern projects, it's more about soft skills than about hard skills. It's more about finding solutions, about explaining your thoughts, about using UML, about presenting your ideas, than about actually writing Java code. Because most of the code is already written, to be honest. So a lot of code already available in open source. A lot of products already on the market as frameworks, libraries, so you don't need to write a lot. More, you need to assemble parts. You need to find the right solution. You need to find the right framework, find the right library, put pieces together and let these pieces work and communicate with other people who will help you out. And these people, in most cases now, are remote. And how to deal with remote people, not by phone calls, but by texting, by explaining your questions, by listening to them in text. And if you have 10,000 Stack Overflow reputation, we understand that you're professional, you have professional soft skills. And on top of that, you also have the Java skills because people, we can check what are the questions and answers you provided there, so we can see that you know something about Java that not so many people know. That's why you made these answers. That's why your answers were upvoted. That's the logic. The same for open source. Why we want people with open source experience? Because we understand that these people can achieve more than others. Usually the question for us the question is, like, I'm trying to answer the question, how to get money 2 times more than everybody else as a salary. If you want money like everybody else, ignore this recommendation. Don't go to Stack Overflow, don't do open source. You will get your salary, just be a good Java programmer. That will be enough. But the question is how to get 2 times more. Why we as an employer, why I would pay you 2 times more than your friend who sits next to you at the same table? You have to show me something, what it is. You cannot type 2 times more lines per hour than your friend. You will type almost exactly the same. You will produce almost the same result. You will write code. I mean, that's the good programmer. You're the good programmer. There has to be a difference, and this difference in these things which I mentioned.
But for someone who has all this knowledge, this experience in this field, and aiming, for example, to get double more the money. But when we talk double more the money, in comparison with all this extra lot of notes that he should do. But on the other hand, here we're just talking about an employee who gets a salary, who gets a fixed salary. Why some people are, let's say, more interested in being an employee than doing their own business? I think most of us have at least one idea in mind for some kind of business or startup or
Yeah, okay. So you're asking why are we...
From my experience, self-work, for example, freelancer makes 3-4 more times
Yeah, I understand. So your question is, why are we talking about employees? Why can't we talk about startup founders or freelancers? Yeah, that kind of a career. Yeah. Well, in most cases, most people will be employees, just statistically speaking. So most of you will end up in large companies and will just work for payroll. That's just statistically speaking. Some of you will be freelancers. Some of you will become startup founders. Maybe one of you will become the next Elon Musk. Maybe. But most of you, 80% of you, will just join large companies and will work for a good payroll. That's just happening. This is what's happening with the world. And actually, I would recommend you to do this. That's my recommendation. So before going to startup, before becoming freelancers, before thinking about how to get the first $1 million and how to get the $1 billion, before you do this, I recommend you to spend 5 years being an employee in a large company. So right after you graduate, you will get offers from big companies. Select the biggest one. That's my recommendation. Select the largest one. Well, ideally come to us. We're probably one of the largest in Russia for sure, in the world for sure. So Huawei is one of the largest companies in the world, and in Russia we are definitely the largest IT company for sure. So it's better to come to the largest IT, one of the largest IT companies, and spend 5 years there. So you will learn the processes, you will see how people work, you will understand the relationship between people and software, you will see how large system being deployed, you will learn a lot of stuff, you will know people, you will understand, they will know you, you will grow some reputation, and only after that, you think about starting your own career as a startup founder, as somebody who is ready to take responsibility for big money.
Can I ask a personal?
Sure, sure.
So, as I read about you from your blog, for example, you have
Yeah, I made it the other way around. I made the mistakes. Of course, I didn't wrong.
no, I mean, for example, you have some your own projects.
Yes.
You are working.
Yes.
Why do you still work? Why do you work in Huawei?
Because I think that I made a mistake, that I started from the wrong, in the wrong order. So I started from startup. I spent a lot of time for trying to be a successful startup founder, and then I realized that the proper way is to first go to a large company and work in a large company and be there and learn the experience and learn what the large company has to offer you. And only after that you try to become a startup founder. So I just decided to do what I'm suggesting to do you now. But you have time. I mean, you're younger. So you're much younger, so you have time to spend 5 or maybe more years. Look at the stories of all these startup founders who are rich. In most cases, I mean, you can exclude like Bill Gates and maybe Elon Musk, but even Elon Musk, he started in a group. He started with he was funded by, I mean, okay, we can scratch Elon Musk, we can forget Bill Gates. But most stories, most successful stories of startups, people go out from Google, people go out from IBM, go out from Oracle. Go out, I mean, they join Google, they work for 10 years, and then they quit and go fund the startup. But first, they learn a lot in Google. They learn a lot how big business is built. And then when you learn and understand this, you get the experience, and then you go out and you know how to build your startup. You need this experience. So that's why I'm suggesting not to try, don't do it yourself, don't learn everything yourself. Just let them teach you first. And then you go for the startup. Okay? That's my personal answer to the personal question. Okay, call to action. In your application, make 1 class, 1 component, 1 deployment, and 3 sequence diagrams. I said it many times. Just do it. Just do it, and you will be extremely bored, but you will learn something. Okay, a few questions, what's unresolved. First one is how to reverse code to model. We asked that already, right? So how to take a code and make the model back. I think this question has no answer for now. How to synchronize the model with the code. Let's say we have the model, we have the code. How to make sure they always stay in sync. Not only from code back to code, but keep them in sync. That's the question, very big. Another one, how to simplify UML for practical programming. UML is a great language, but it's still not being used for practical programmers. Most programmers still draw these funny, nice Microsoft Visio diagrams. So how to make UML more accessible, more attractive, more easy to use? I don't know. And the final one, how to restore faith in a model-driven architecture. I don't believe in it, so maybe something should happen that I will still start believing in this paradigm. I don't know what it should be. That's for you, the future. Think about this. That's it for today. Thanks for coming. See you in 2 weeks.